Hello everyone and welcome to the next episode of GPU Programming with TNL. In today's video we will talk about dense matrices. Matrices, along with vectors, are among the most important objects in mathematics. A matrix is essentially a table of numbers that can have different meanings depending on the problem we are solving. Here are a few examples. Tables in Excel or Pandas can be understood as matrices if they contain only numerical values. Matrices represent linear transformations in mathematics and physics. For example, in computer graphics, they enable operations like rotation and translation of objects in 3D scenes. Matrices also represent systems of linear equations, which are often solved in computer simulations. Matrices are fundamental in statistical data analysis, where they represent data sets, and in machine learning, where they form the basis for constructing neural networks. In graph theory, matrices are used to represent graphs. Various graph algorithms are applied, for instance, in the analysis of social networks or computer networks. One of the fundamental classifications of matrices is into dense and sparse matrices. The distinction has almost no significance from a mathematical or theoretical perspective, but it is very important for programmers. For dense matrices, we store all their elements in memory. On the other hand, for sparse matrices, we assume that many or even a significant majority of the matrix elements are zero, so we store only the non-zero elements. This brings several complexities, especially when programming for GPUs, but it allows us to work with much larger matrices. Consider the following example. If a matrix has dimensions of 50,000 rows and 50,000 columns, it will have a total of 2,500,000,000 matrix elements. If we store these elements in memory as the float type, which requires 4 bytes per element, we would need 10 gigabytes of memory. However, if this matrix was sparse and had, for instance, only 3 non-zero elements per row, while all other were zeros, it would contain only 150,000 non-zero elements. Storing these non-zero elements would require just 600 kilobytes of memory. Including the necessary auxiliary data required by formats for storing sparse matrices, the total memory requirement would be approximately 1.2 megabytes. In a real-world task, we often need to work with matrices that have dimensions in the millions of rows and columns. In today's episode, we will focus solely on dense matrices and leave sparse matrices for next time. In TNL, a dense matrix is represented by the templated class dense matrix. This class has several template parameters. The first parameter, real, specifies the numeric type of the matrix elements. The second parameter, device, specifies the device where the matrix should be allocated. The third parameter, index, determines the type used for indexing the matrix elements. The last parameter, real allocator, is the allocator for matrix elements, which has a default setting and usually does not need to be specified explicitly. I skip the fourth parameter, organization, which specifies the organization of matrix elements in memory. These elements can be stored either row-wise or column-wise, as shown in this illustration. Row-wise storage means that the first row is stored as a contiguous block of data in memory, followed immediately by the second row and so on for subsequent rows. Column-wise storage works similarly, with the first column stored as a contiguous block of data in memory, followed by the second column and so on. Row-wise storage tends to be more efficient for CPUs, while column-wise storage is often better for GPUs. This is the default configuration, but you can easily change it to suit your needs. In what follows, we will demonstrate several ways to set matrix elements. This step is always the first thing you need to do before performing any other operations on matrices. If the matrix is stored on the CPU, this process is relatively straightforward. On the GPU, it is slightly more complex. In such cases, you can choose between a simpler but less efficient approach where you construct the matrix on the CPU and then copy it to the GPU, or directly constructing the matrix on the GPU, which is slightly more complex but significantly more efficient. First, we will demonstrate how to create a new matrix using an initializer list. This is a very simple method, but it is suitable only for small matrices known at compile time. Everything is shown in the example 01 initializerlist.cu. In the function initializerList example, we see two ways to create a full matrix. On lines 8 to 14, here, we create a classic dense matrix with 3 rows and 6 columns. On lines 19 to 27, which is here, We then create a so-called lower triangular matrix, which is a matrix where all elements above the diagonal are 0. In its definition, we don't need to specify those elements. They are automatically filled with zeros, and in memory, this matrix is stored as a regular dense matrix, including the 0 elements above the diagonal. We can compile the example using TNL CXX and run it. The program creates both matrices on the CPU and GPU and prints them all to the console. We can observe that for the triangular matrix, for example here, the 0 elements above the diagonal are indeed stored in memory. In real-world tasks, we often work with much larger matrices whose elements are generated at runtime. The simplest way to construct such a dense matrix is by using the methods setElement or addElement. The use of both methods is demonstrated in the example 02 setElement.cu. The setElement method sets the value of a matrix element at a given row and column. The addElement method works similarly, but instead of replacing the current value, it adds the provided value given as the third parameter to the existing value of the matrix element at the specified row and column. If a fourth parameter is provided, the original value of the matrix element is first multiplied by this parameter, and only then is the specified value added. The use of the setElement method is shown on line 9, where we set the diagonal elements of the matrix to value 2, and the use of the addElement method is demonstrated on line 15. Here the original value of the matrix element is first multiplied by 3, and then 1 is added to the result. This method of setting matrix elements is efficient on the CPU. However, if the matrix is allocated on the GPU, each individual matrix element is transferred separately between the CPU and GPU, which is highly inefficient. Therefore, this approach is recommended only for smaller matrices or when the speed of matrix construction is not critical for the application. Again, we may compile the example using TNL CXX and run it to see that firstly we set just the diagonal elements of the matrix to 2, and then we multiplied all matrix elements by 3 followed by adding 1. The example 03 setElement.direct.cu demonstrates how to efficiently set matrix elements directly on the GPU. It utilizes the parallel for function for parallel traversal of matrix elements. Since a matrix is essentially a two-dimensional table of numbers, we will need to use the two-dimensional variant of the parallel for function. We didn't cover this variant in the episode on lambda functions and parallel for. By the way, if you haven't seen the episode and are unfamiliar with the use of lambda functions or the workings of parallel for loops in TNL, I highly recommend watching it. You can find the link below the video. The multidimensional parallel for function iterates over a range of multidimensional indices. These ranges are represented by the type static array, and we first define a type alias coordinates for it, here on line 11, which serves as a two-dimensional static array. The dimension is given by the first template parameter here. Next, we create an instance of dense matrix having 5 rows and 5 columns. Since we need to access the matrix within the body of the for loop, we also create an instance of matrix view here on line 13, which functions similarly to array view or vector view. Then on lines 15 to 21, we implement a lambda function that sets the individual matrix elements. This lambda function is invoked by the parallel for and receives a single parameter of type coordinates here. It represents the coordinates of the matrix element. For better clarity, we define aliases row IDX for the first component of the matrix element's coordinates and column IDX for the second component. Next, we calculate the value of the given matrix element and store it in variable value here. We then use the method setElement of the matrix view object. This method automatically detects whether it is being called directly on the GPU, and if so, it can set the matrix element value directly without copying between the CPU and the GPU. The addElement method works similarly. We then prepare variables begin and end to define the range of indices for the matrix elements we want to iterate over in the parallel for loop. Finally, we call the parallel for function passing it the begin and end coordinates. From their type, the function recognizes that it needs to iterate over two-dimensional range of indices. Of course, we also pass the prepared lambda function f. Lastly, we print the matrix to the console here. We can compile using TNL cxx and run it. In the output, we can see that the matrices are correctly set. The example 04 4elements.cu demonstrates how to achieve the same functionality as in the previous example, but in a slightly simpler way using the 4elements method here. This method is part of the interface of both the dense matrix and dense matrix view objects. With this method, we specify a range of rows to iterate over here, and for all matrix elements in those rows, it calls the provided lambda function, this one. This function can then manipulate the individual matrix elements. If we want to iterate over all rows of the matrix, we can use the for all elements method, which does not require specifying a range of row indices. The lambda function f now directly receives the following parameters: row ID x, which is row index, column ID x, which is column index, a global ID x parameter, which we can ignore for now. It is used for compatibility between dense and sparse matrix interfaces, and finally, a reference to the respective matrix element. In the body of the lambda function, we can directly modify the value of the matrix element here. The advantage of this approach is that we do not need to create any matrix view instance. We can compile using TNL cxx and run it. In the file 05 benchmark.cu, we find code that compares the various approaches and measures their efficiency. We won't go through the source code itself here, as it is based on techniques from the previous examples. The benchmarking is conducted on square matrices of varying sizes. The benchmark includes the following measurements: the time it takes to construct the matrix on the CPU, the time it takes to copy the same matrix from the CPU to the GPU, the time it takes to construct the matrix on the GPU using the setElement method but calling it from the CPU, meaning each matrix element is copied individually to the GPU. The time it takes to construct the matrix on the GPU using the parallel for function, which means that the setElement method is called directly from the GPU. The time it takes to construct the matrix on the GPU using the forelements method. The results are summarized in the following table. The column size sets the dimensions of the matrix. On the CPU, all the previously mentioned approaches have more or less the same efficiency, and the table represents them by measuring the efficiency using the setElement method. If we construct the matrix in the same way on the GPU, this approach becomes highly inefficient, especially for large matrices. As mentioned earlier, the reason is that each matrix element is copied individually between the CPU and GPU, which is very inefficient. Now let's compare this approach with a situation where we first construct the matrix on the CPU using any method and then copy the entire matrix to the GPU. We can see that this approach is significantly more efficient. This is because in this case, all the matrix elements are copied from the CPU to the GPU as one contiguous block of data, which can be done much faster. This approach is particularly suitable in scenarios where we need data available on the CPU to construct the matrix. Finally, the table lists the times for constructing the matrix directly on the GPU, whether using the parallel for function along with the setElement method called directly from the GPU, or using the forelements method. Both approaches yield the same times, and we see that they are the fastest of all the mentioned methods. Therefore, choose these methods in situations where performance is absolutely critical. In the next example, 06 matrixwrapping.cu, we demonstrate how to create a dense matrix view that wraps around existing data. This can be useful when you want to leverage TNL's functionality in an existing project. In this example, we first create an array containing the matrix elements here. For simplicity, we use a TNL vector, but ultimately we consider a standard array represented by a pointer to the first element, as is common in plain C, which we can see here. We then use the wrap dense matrix function here, passing it the matrix dimensions here and the pointer to the array of matrix elements. This function also accepts a template parameter that specifies the device on which the data is allocated here, the type of matrix elements, here it's double, indexing type, here it's integer, and ordering of the matrix elements. In our case, we use row major ordering. The function returns a dense matrix view, which can then be used just like a regular matrix. We can again compile using TNL CXX and run it. And we see that it works as expected. Many matrix operations are based on row-wise reduction. A classic example is matrix vector multiplication. Here we have an example of multiplying a matrix A with vector X, resulting in a vector Y. The multiplication proceeds as follows. We take the elements from the first row of the matrix, multiply them by the corresponding components of vector X, and then sum them up. The result is the first component of vector Y. We then perform the same operation with the second row of the matrix A to obtain the second component of vector Y. Finally, we repeat the process with the third row of matrix A to compute the third component of vector Y. To enable users to easily implement custom operations with matrices, TNL provides the ability to perform general reductions on matrix rows, similar to what we demonstrated in the last episode on parallel reduction. This is illustrated in the example 07reducerows.cu, specifically with the example of matrix vector multiplication. First, we create a suitable matrix and then vector X and Y. All components of vector X are initialized to 1. Next, we prepare the necessary vector view objects xy and yy for vector X and Y, along with lambda functions fetch and keep. The fetch function, like in basic parallel reduction, is responsible for retrieving the data to be reduced. It is called for each matrix element and receives 3 parameters. Row IDX is the index of the matrix row, column IDX is the index of the matrix column, and value is the value of the matrix element. Since we want to compute the product of the matrix and vector X, we must multiply the value of the matrix element by the corresponding component of vector X, whose index matches the column index of the matrix element, which is the value of the variable column IDX. Unlike basic parallel reduction, matrix reduction also uses keep function, which is responsible for storing the results of the reduction in each row. It is called for each matrix row and receives 2 parameters. Row IDX is the index of the row for which the reduction was computed, and value, which is the result of the parallel reduction for that row. In our example, the result of the reduction is stored in vector Y at the position corresponding to the row index. Next, we call the reduceRows method, providing the following parameters. The range of row indices for which the parallel reduction should be performed. Since we want to compute reductions for all rows, we specify the range as 0 to matrix getRows, which is the number of rows in the matrix. Alternatively, we could directly call the reduceAllRows method, which performs the reduction for all rows and does not require specifying a row index range. Next parameter is fetch lambda function for retrieving data for the reduction. Next parameter is the functional used for the reduction. In this example, it performs addition, but other functionals or custom lambda functions can be used as in basic parallel reduction. The last parameter is the lambda function keep that stores the result of the reduction for each row. Finally, we print the matrix, input vector X, and output vector Y. Now, we may compile and run the program, and we observe that the results are correct on both the CPU and the GPU. Let's look at another example of row-wise reduction in matrices. This time we will compute the maximum of the absolute values of matrix elements in each row. The example can be found in the file 08maxinrows.cu. Instead of vector X and Y, we now use vector rowmax, which has as many components as the matrix has rows in this example. Regarding the lambda function definitions, the fetch lambda function now simply returns the absolute value of the matrix element for which it is called, and the keep lambda function writes the result of the reduction from each row into the output vector rowmax using the vector view rowmaxView. We call the reduceAllRows method of the matrix, passing the custom lambda functions along with the functional TNL max, which ensures the computation of the maximum absolute values of the matrix elements in each row. Finally, we print the resulting vector. We may compile and run the example to see that the output appears as expected. Basic matrix operations such as matrix vector multiplication, matrix-matrix multiplication, the addition of two matrices, or matrix transposition can all be performed with matrices. All these operations will be demonstrated in the following examples. We begin with the operation of matrix vector multiplication, which is among the most commonly used operations. The vector product method of the dense matrix and dense matrix view classes computes the expression y equals alpha ax plus beta y. The first four parameters of this method are vector x and y, followed by the parameters alpha and beta. The last two parameters begin and end allow specifying the range of rows for which the product will be computed. If both parameters are set to 0, which is the default setting, the product is computed for all rows. The operation of matrix vector multiplication is demonstrated in the example 09 matrix vector product.cu. This is a modification of the example 07 reduce rows.cu, but instead of performing a parallel reduction across rows, we directly call the vector product method, which computes the matrix vector product. First, we prepare matrix A, the input vector x, the output vector y. All components of the vector x are set to 1, and then we print the matrix A and vector x. Next, we calculate the product A times x, store the result in vector y, and print the vector y. Next, we demonstrate how to compute the expression 1/2 times ax plus y using suitable values for parameters alpha and beta, which is 1/2 and 1, and we print the result again. The example can be compiled using TNL cxx and executed. The multiplication of two dense matrices is performed using the getMatrixProduct method of the dense matrix class. This method computes the expression result equals alpha times b times c. The first parameters of this method are the matrices b and c, followed by the parameter alpha. Additionally, you can specify whether either the matrices b or c should be transposed during the multiplication. This transposition is performed on the fly and does not modify the matrices b or c themselves. The code demonstrating the multiplication of two dense matrices can be found in the file 10 matrixproduct.cu. In this example, we first create matrices b and c and print them to the console. Then we compute the product of matrices b and c and store the result in matrix A and print the matrix A to the console. Finally, we demonstrate the multiplication of the transposed matrix B with matrix C. The result is again stored in matrix A and we print it to the console. The example can be compiled, executed, and the multiplication results are displayed as expected. Matrix addition can be performed using the addMatrix method of the dense matrix and dense matrix view classes. This method computes the expression A equals alpha b plus beta a. The parameters for this method include matrix B, coefficients alpha and beta, and a flag to specify whether matrix B should be transposed before being added. This transposition is performed on the fly without modifying matrix B itself. The code demonstrating this method is in file 11 matrixaddition.cu. In this example, matrix A and matrix B are created and printed to the console. Next, matrix B is added to matrix A and the result is printed to the console. And then transposed matrix B is added to matrix A and again result is printed to the console. We can compile the example and execute to see the result. Matrix transposition can be understood as a rotation of matrix elements around its diagonal. The transposed matrix is obtained by swapping the row and column indices. In TNL, transposition can be performed using the getTransposition method of the dense matrix class. Along with transposition, this method can also multiply the matrix element by coefficient alpha. The method takes as parameters the input matrix B, coefficient alpha, and the resulting transposed matrix is computed and stored in matrix A. If you want to transpose a square matrix, you can perform an in-place transposition, which requires no additional memory and overrides the original matrix with its transpose. This operation is performed using the getInPlaceTransposition method of the dense matrix class. This method can also multiply the matrix by a coefficient alpha, which is its only input parameter. Both methods are demonstrated in the example in the file 12matrixtransposition.cu. In this example, a matrix A is created with all elements above diagonal set to 0, which is a lower triangular matrix. The matrix is printed to the console. The transpose of matrix A is stored in matrix B, and matrix B is printed to the console. And finally, an in-place transposition of matrix A is performed, and the matrix A is printed to the console. Now, we can compile the example and execute it, and we see the result. As a final note, I'd like to mention one more thing regarding the API for dense matrices. In the future, it is very likely that some changes will be made to the interface for working with matrices in TNL. One such change involves replacing certain methods of the dense matrix and dense matrix view objects with free functions. For example, the forElements method will likely be replaced by the function TNL matrices for elements. Similarly, other methods such as reduce rows, vector product, get matrix product, add matrix, get transposition, and get in-place transposition may also be replaced by corresponding free functions. The original methods will, of course, remain available for some time, but will be marked as deprecated. And that's all for today. Thank you for your attention. I hope you have learned something useful, and in the next episode we will focus on sparse matrices. Until then, happy coding!